Hello and welcome to this video. For this one, we're going to write some exponential functions from word problems and see how that works. So in this first one, we have an experiment Kristen is doing with 7,500 bacteria cells, and after 4 hours, there are 23,000 cells. Our first goal is to write an exponential function that could be used to model the number of bacteria after X hours, assuming it changes at the same rate, right? Because it says exponential function, we're going to go ahead and use our growth function from 8-1. Essentially, it's f of x, or y, right? Y is equal to the initial amount, right, times your growth rate to the x, right, where x is the number of times it has grown, or usually independent variable is time. So here, 1x, x would be hours. X would be hours. A is going to be your initial amount, right, of bacteria. And y is your, final amount, or the amount after a certain amount of time, right? So our goal is to figure out what b is right now, because we want the growth rate. Growth rate, essentially. So let's plug in the numbers. We have 23,000 at the end of the 4 hours. We started with 7,500, so that's our initial amount. We don't know our growth rate, but we do know that 4 hours has passed. And now we're just going to solve for b. So divide both sides by 7,500. And we get 3.07, we'll round, is about equal to b to the 4th. And to solve that, we'll just take the 4th root of both sides. So the 4th root of 3.06666667, and we get b being equal to about 1.32, right? 1.32. And let's just go ahead and take some more decimals there to be very specific. That's equal to b, 1.3233. Okay, so now we have an equation for the number of bacteria after a certain amount of hours. An approximate equation. We think that the total amount of bacteria will be equal to your initial amount, in this case 7,500, times 1.3233 to the x hours. Okay, so we could graph this if we wanted to, that sort of thing. But all we want to do is figure out part B, which says how many can be expected in the sample after 12 hours. So for B, we're just going to take that and do 7,500 times 1.3233 to the 12th power, because it's been 12 hours. So hit enter there. 1.3233 to the 12th power, and we're going to multiply that by 7,500, and we get quite a large number, so 216,252.44. Alright, so quite a bit of bacteria. sweet. You may have gotten a slightly different answer if you rounded to a different place than I did. All right, but that is good. I'm confident there and here. All right, for the second word problem, we'll look at this. Manufacturer distributed 3.2 million aluminum cans in 2005. Sorry for the cutoff there, 2005. All right, in 2010, so 5 years later, the manufacturer distributed 420,000 cans made from the recycled cans it had previously distributed. Assuming that the recycling rate continues, write an equation to model the distribution each year of cans that are made from recycled aluminum. All right, so this one, instead of being growth, would be decay. But that is actually the same exact initial equation. You're just expecting your b to be less than 1. So y equals a times b to the x. All right. Also, you have to make sure you put your numbers in the right place. In this case, the final amount is 420,000, right? Because we're looking sort of at their ability to recycle, and it's also clear it's the final amount because it's 5 years later. So that's equal to the initial amount. They had 3.2 million, so 3,200,000, right? Times some growth rate, and I'm going to use 1 year for the time period, and I'll put a 5 there. Okay, but you could also use 5 years as one time period since Part B uses 2050. But let's take a look and see what happens. So the first thing I'm going to do is divide both sides by 3.2 million. So 3,200,000, 3,200,000, right? By. So essentially, it's 40. Oh, changing all my answers there. 42 divided by just 320. Okay, and I get 0.13125. So 0.13125. Okay, and that equals b to the 5th. Of course, next I'm going to take the 5th root of both sides to solve for b. So I want to do 5th root of 0.13125. Right? And I get 0.67. We can round that one off there, and that's equal to b. So we have our equation. We have y is equal to 3,200,000 times 0.67, right, to the x, where x is years for us, right? X is in years. All right. One thing I will say, you do have the option here, as long as you notify whoever you want to notify, to put this in millions, right? So you could also say this is y is equal to 3.2 times 0.67 to the x, as long as you remember to tell, this would be in millions. All right, so they'll have to know to fix that at the end of the problem. All right, so for part B, how many cans made from recycled aluminum can be expected in the year 2050? So I'll put this sort of over here, right? For part B, what I want to do is just use the equation and put the number of years that has passed for my x. So I'm going to do y is equal to 3200,000 times 0.67 to the, and it's from the original year, 2005, so it's been 45 years since then. So let's see what we get. 0.6, oh, gotta start hitting enter. 0.67 to the 45th power. We're getting a very small number there. We're going to multiply that by 3200,000. And our answer is, by that year, we will have 0.05. So that would be none. That'd be no cans from the original aluminum.